Hello viewers, so welcome back to the course on matrix computation and its application. So in the previous lecture we have discussed few examples about how we can find the rank and the nullity of a linear transformation. So today we are continue with that one. So I know that if I have the linear transformation from U to V, so suppose this be a linear transformation, then the dimension of RT is called rank of T, and also sometimes we represent by RT, and dimension of null space NT, that is called the nullity of T, that sometimes we represent by a small nt. So this one we have discussed. So let's take one example. Suppose I take a linear transformation T from V4 to V3. In the previous case we have taken a transformation from V3 to V4. Now we are taking from V4 to V3 by the transformation T. So we are representing it is x, y, z, t. Suppose I am taking this equal to x minus y plus z plus t, x plus 2z minus t, and x plus y plus 3z minus 3t. So this is my linear transformation. So that is a linear, so that we already know. Now we need to find rank and nullity of T. So this one we need to find. Now from here I know that the range space is made up of this type of elements. So now I can write from here that I can write my x minus y plus z plus t, x plus 2z minus t, x plus y plus 3z minus 3t. This one I can write as x I can take common. So I can write here it is 1, 1, 1. Then I can take y common. So y common it will be minus 1, 0, 1, z it can be written as 1, 2, 3, and t. So it can be 1, minus 1, minus 3. And if you see from here, now this is equal to my t of x, y, z, t. Now from here I can write this as, so this one I can write as, I will take a matrix with first vector as a first column, then minus 1, 0, 1, 1, 2, 3, and 1, minus 1, minus 3. And from here I can write x, y, z, t. So you can see from here that this is 3 cross 4 matrix, it is 4 cross 1, and this is equal to t of x, y, z, t. This I can write as a x. So it is equal to x, y, z, this one. So now from here you can see that this t, the transformation, basically we are able to represent this t with this matrix, and this matrix is of order 3 cross 4, and t is a linear transformation from V4 to V3. So we are able to represent this transformation in terms of this matrix. Now from here I know that So, this is my equation number 1. Now, from here I can say that my RT range space is spanned by these vectors. (1, -1, -3). But the range space I know that is a subspace of V3. Since RT is a subspace of V3. So, it has a 4 vector in its span. So, definitely it cannot be linearly independent, and also it belongs to V3. So, from here I know that. So, now I need to check that how many vectors are linearly independent in this case. So, I will take this matrix. So, now the corresponding matrix I have 1 1 1, next is -1 0 1, -1 0 1, 1 2 3, and the next is 1 -1 -3, 1 -1 -3. So, this is the matrix we are having. Now, I will reduce this into the echelon form. So, I will write minus of R1 R2 minus of R1 plus R3. So, I can write 1 -1 1 1. So, this becomes 0 and this is also becoming 0. So, I am multiplying with -1. So, it will be 1, -1 plus 2, it is 1. So, -1 and -1 minus 2, then it is -1 and the 1 plus 1 2, -1 plus 3 is 2, and -1 minus 3 minus 4. So, I am getting this value. Now, from here I will, so this is my pivot element, this is my pivot element. So, I will put -2 R2 plus R3. So, this is 1 0 0 minus 1 1. So, this will become 0, 1 1 1 minus 2, and now I am putting -2 plus 2, that will be 0, and minus 2. So, it will be 4 minus 4, that will be 0. So, I am able to get, this is my pivot elements. So, I know that these two vectors are basic columns and this is a non-basic column. So, from here I can see from here that the rank of this matrix, so let call it, maybe I call it A. So, rank of this matrix A is 2, that we can check from here. Also, I can write this non-basic column, this and this. So, I can write this 1 1 0, I can write this 1 1 0 as 2 times of 1 0 0 plus -1 1 0. So, 2 minus 1 1, then 1 and then 0. So, this is the way we can find this one, and also I can write 1 minus 2 0. So, this one I can write as minus 1 0 0 minus 2 minus 1 1 0. So, it is -1 and it is 2. So, it will be 1 and then it is -2 0. So, this non-basic column can be written as a linear combination of the basic columns. So, from here I can find that the set 1 1 1, the first and the next one -1 0 1. So, this the whole this one they span the whole RT and they are linearly independent. So, from here I can say that the rank of my linear transformation is 2. Now I want to find the nullity. So for nullity, this is my image, so I will put this image equal to 0. So now I need to put the image, so that image is x minus y plus z plus t, that is equal to 0. Then x is x plus 2z minus t, that is equal to 0, and x plus y plus 3z minus 3t equal to 0. So, these are the three conditions. Basically, I am putting this element equal to 0, this and this one. Now, from here I have 4 variables and 3 equations, and I know that the rank is 2. So, now from here there is no need to convert this one into the echelon form, because we can use this matrix here. So, I will use this matrix, and from there I will get that we can have x minus y plus z plus t 0, and I can have x plus z minus 2t equal to 0. So, I can, with the Gauss elimination, I can convert this into this form, because the rank is 2. So, this is the way we can find out. Now, from here I can write my, suppose I just take t from here. So, I can write from here that x plus z is equal to 2, and I will put this value here in t. So, I can write my, maybe I will write z in terms, because it is a rank is 2, number of variable is 4. So, free variable is 2, free variables is 2. So, that z I can write as minus x plus y minus t. So, this is minus x plus y minus t is x minus z by 2, or maybe I can write here plus. So, this is my t. So, that becomes minus 2x plus 2y minus x minus z divided by 2, and I can write from here that this is equal to, so minus 2x and minus x, so minus 3x plus 2y minus z now z, instead of z I also need to put this value. So, maybe I have put t is equal to xz. So, maybe I will, because I need to convert this into this form. So, I can write, what should I will just take y. From here I will take, I can take my y is equal to x plus z plus t. So, that is okay. So, I can write x plus z plus t is x plus z by 2, and that gives me, so 2x plus x 3x and 2z plus z 3z by 2. So, this is the way we are able to write our variable. So, now from here x, y, z and t. So, this is my vector. It can be written as x, y is 3x plus 3z by 2. So, 3x plus 3z by 2, z, and t I can write x plus z by 2, x plus z by 2, and from here I can write my x as 1, 3 by 2, 1 1 by 2 plus z 0 3 by 2 1, no it is 0 basically, x x x, and z is coming from here 3 by 2 1 and 1 by 2. So, and also I know that from here these two vectors are linearly independent, because here it is the 0 element and here is 0 element. So, I cannot make this element 0 by a scalar multiple. So, from here I can write that the null space is spanned by, so from here just I can write that the nullity of T is 2, and the null space is spanned by this vector. So, I can write that NT is spanned by 1 3 by 2 0 1 by 2 one vector, and 0 3 by 2 1 1 by 2 another vector, and this is belongs to, definitely we know that this is subspace of V3. So, belongs to V4, sorry, because we have a linear transformation from V4 to V3. So, from here also we can check that the rank plus nullity, that is 2 plus 2 is equal to dimension of V4, that is 4. So, based on this one, now we are going to introduce a very important theorem, and that is called the Rank-nuility theorem. So, we are going to introduce a Rank-nuility theorem. So, what is this Rank-nuility theorem? Now, let I have a linear transformation from U to V be a linear transformation and U be a finite dimensional vector space. Then rank of T plus nullity of T is equal to the dimension of U. So, this is called the Rank-nuility theorem. You can check from here that although the range space is a subspace of V, but the rank plus nullity satisfy this condition. So, this is a very important theorem. We can prove this one. So, I can assume that let dimension of U is maybe n, let this one. Also, dimension of NT, the nullity, let it is equal to k. So, this is we have decided, and also we know that the k will be less than equal to n, because null space is a subspace of U. So, definitely the dimension of NT is always less than equal to the dimension of U. So, that is true. Now, it is given to me that null space is having the dimension k, that is the nullity is k. So, let we take a base B U1, U2 up to UK. So, let B be a basis of null space T. So, if it is a basis of this, then we know that T of U1 T of u2 all are going to be T of uk all are going to be 0, because this is belongs to the null space. Now, since NT is a subspace of vector space U, then by extension theorem we can extend the basis set B. So, this is the basis of NT to a basis of U. So, that we can do. So, let I just take B1 is the basis. So, that will contain U1, U2, UK, UK plus 1, UK plus 2, because this is the it is equal to UN. So, let B1 be a basis of U. Now, so that this we have shown. Now, consider a set. So, I consider a set A. What is this set? This set is I am taking T of u k plus 1, T of u k plus 2 up to T of u n. So, this A contains n minus k elements. Okay. So, I consider the set A. Now, we need to prove that A is a basis of range space R T. So, to prove this one, what I need to do? First, I need to show that A, this A basically, yeah. So, that is I need to show that the span of A is equal to R T, and the second one I need to check that A is linearly independent. So, if this set of A I have taken is linearly independent and it spans R T, then we can say that this is the basis of R T. So, how we can do that one? So, let us prove this thing, two things. So, the first one, so this I need to prove. Now, so what I am going to do? So, let now A span means the span of T of u k plus 1, T of u k plus 2, T of u n. This is. Now, since T of u k plus 1, T of u k plus 2 and all this T u n, they belongs to the range space T, and the range space of T is a subspace of the vector space V, then from here we know that their linear combination T of u k plus 2. So, if I take their linear combination that are contained in range space of T, because their linear combination also belongs to R T. So, if I take the set of all the linear combination, that is basically span, this is contained in R T. Now, so after doing this one, so this is the one way I have done. Another way I can say that let some V belongs to R T. So, this I can write as 1. So, let I take a V from R T, then there exists some u belongs to u such that T of u is V. Now, V belongs to R T. Now, so what I need to show is that I want to show that for any V I have taken from R T, there is a u from the u so that T u is equal to V. Now I want to show that V belongs to the span of this one. So, this one I need to show. So, if u belongs to u, now since B1, since the set B1 is a basis of u, then I can write my u as a linear combination of alpha 1 u1 plus alpha 2 u2 alpha k uk alpha k plus 1 uk plus 1 alpha n un. So, I can write like this one, and this is linearly independent. So, all alpha i's are uniquely determined because they are linearly independent. So, this is the only unique representation of u. I can write from here, and all alpha i's are scalars. Now, from here I can write my T u. So, T u becomes T of alpha 1 u 1 alpha k u k alpha k plus 1 u k plus 1 alpha n u n. So, this one we have written. So, this can be written as alpha 1 T of u 1 plus alpha 2 T of u 2 alpha k T of u k plus alpha k plus 1 T of u k plus 1 T of u n. So, I can write like this one. Now, from here you see that this is equal to 0, this is equal to 0, because I know that u 1 u up to u k are the bases of n t. So, its image will be 0. So, this will be 0. So, from here I can write that this is equal to alpha k plus 1 T u k plus 1 up to alpha n T u n. It means that the T u, and that is my V, can be written as a linear combination of this one. So, from here I can say that V belongs to the span of T of u k plus 1, T of u k plus 2, T of u n, and from here I can say that my R T is subset of this one. T of u n. So, from 1 and from 2, we can say that the range space of T is equal to the span of A, because this is A basically, this one. So, we are able to show. Now, we need to show is second one, that A is linearly independent. So, that we need to show. So, for this one, let I take a linear combination. So, I just take linear combination as alpha k plus 1 and T of u k plus 1, this one, plus alpha k plus 2 T of u k plus 2 alpha n T of u n, that is equal to 0. So, this linear combination I take and put equal to 0. Now, so I need to show that this A is linearly independent. It means we need to show that all this alpha k plus 1, alpha k plus 2 up to alpha n all are 0. Now, from here I can write that T of alpha k plus 1 u k plus 1 k plus 2 alpha n u n, that is equal to 0. So, if it is equal to 0, which implies that alpha k plus 1 u k plus 1, this combination alpha n u n, that belongs to null space of T, because their image is going to 0, and this 0 is basically a 0 of V. So, that we already know that this belongs to the 0 of V. Now, I know that if it belongs to NT, then the null space having the basis B. So, from here that since B is a basis of NT, so now we can write that alpha k plus 1 u k plus 1 alpha n u n can be written as a linear combination as alpha 1 u 1 alpha 2 u 2 alpha k u k, and from here I can write that I can take this on the right hand side. So, I will get alpha 1 u 1 plus alpha 2 u 2 alpha k u k minus alpha k plus 1 u k plus 1 minus alpha k plus 2 u k plus 2 minus alpha n u n is equal to 0. So, these things we got, and this 0 is from U now, because NT is a subspace of U. So, I know that this is equal to the. Now, if you from you can see that u 1 u 2 up to u k plus 1 u k plus 2 u n. So, if you check from here, then this is basically a basis of U. Now, since B 1 that contains u 1 u 2 u k plus 1 u n be a basis of U. So, now from here, which implies that alpha 1 alpha 2 up to alpha k plus 1 up to alpha n all are 0. So, this is all are 0 because this is the basis element, and from here which implies that alpha k plus 1 alpha k plus 2 alpha n all are 0, and from here I can say that the set T of u k plus 1, T of u k plus 2, T of u n, this set is linearly independent. So, now we are able to show that this is linearly independent and it spans R t. So, from here I can say that A, that is T u k plus 1, be a basis of a basis of R t, because this is what I wanted to show, that this set A is basis of R t. And now from here you can say that is the basis of R t. So, dimension of R t will be n minus k, and from here, so dimension of R t is the rank, basically it is the rank of t. So, from here I can write that rank of t plus this k is the nullity of t, and that is equal to n, where n we have taken that n is the basis of dimension of u. So, that is equal to this one. So, from here we can able to show that the rank plus nullity, that is equal to the dimension of the space u whenever we have a linear transformation from u to v. So, this is a very important theorem for in the case of rank nullity. So, we will stop here now. So, in the today's lecture we have discussed a very important theorem, that is the rank nullity theorem. So, that shows that if we have a linear transformation T from any vector space, finite dimensional vector space u to v, then the rank of T plus the nullity of T, that is always equal to the dimension of the vector space u, and it is very useful theorem. We can use this theorem in future to solve many problems. So, I hope that you have enjoyed this lecture. Thanks for watching. Thanks very much.